The next time you fly over a city, picture its rivers snaking through neighborhoods or coastlines hugging the skyline. Now, imagine the stark contrast of a barren desert below. These patterns aren't random. Geography shapes where life thrives. Why do some places teem with millions while others remain desolate? From the lush Nile Delta to the arid Atacama Desert, the answer lies in three key geographical factors. These silent forces dictate where humanity flourishes or fades. The story of our cities and settlements is written in the land itself, an enduring mystery that reveals how the world we know came to be. The stark contrast that defines humanity. Here are two satellite images showing our planet at night. One shows Dhaka, Bangladesh, where 44,500 people squeeze into every square kilometer. The other shows Greenland, with just 3 people occupying that same space. These places, separated by only 20 degrees of latitude, illustrate a staggering population density difference of 1.5 million times. This pattern isn't new. Historical records reveal similar trends. The Indus Valley supported dense settlements 5,000 years ago on its fertile floodplains, while nearby deserts remained empty. Ancient Rome clustered by the Tiber River, yet the Italian Alps stayed sparsely populated. These examples highlight consistent geographic rules that have shaped human settlement for millennia. Many believe population distribution reflects political boundaries or cultural preferences, but the data tells a different story. Over 90% of humans live on just 10% of Earth's land surface, clustering in areas dictated by environmental factors rather than borders. For instance, the Ganges River basin occupies less than 0.1% of India's land area, but houses 1/3 of its population. Water access is a key driver of this disparity. Dhaka, situated between the Ganges and Brahmaputra rivers, benefits from constant freshwater, fertile silt deposits, and transportation routes, 3 essentials for survival. In contrast, Greenland's ice sheet locks water underground for most of the year, making large-scale habitation nearly impossible. This reliance on water dates back to humanity's earliest permanent settlements. Archaeological evidence shows cities like Memphis, and Mohenjo-Daro all emerged within floodplains. Modern statistics confirm the trend. Countries with river access average population densities 7 times higher than those without reliable freshwater. This explains why some regions sustain dense populations for thousands of years while others remain barren. The Nile Valley, for example, has supported human habitation for 7,000 years due to its annual floods, which renew soil fertility and ensure water security. Meanwhile, the Atacama Desert, receiving less than 1 millimeter of rain per decade, remains one of the planet's emptiest places. The Ganges River offers a striking modern example. This single waterway supports 400 million people, more than the entire population of North America, within its basin. The surrounding lands produce crop yields 3 times higher than India's national average, with rice harvests 50% larger than those in rain-fed regions just a few hundred kilometers away. Water's influence extends beyond agriculture. Manufacturing clusters near rivers for cooling systems and waste disposal. Cities depend on rivers for drinking water and sewage processing. Historically, waterways served as the most efficient transportation routes for bulk goods. Even today, over 50% of international trade moves by sea, underscoring water's enduring role in development. In contrast, water-scarce regions struggle to sustain populations. Australia's interior, covering 70% of the continent, houses just 2% of its people. The American Southwest relies on unsustainable groundwater extraction to support cities like Phoenix, where evaporation rates exceed annual rainfall. These exceptions highlight the broader geographic rule. Recent studies quantify this relationship across 150 countries, showing that a 10% increase in available freshwater correlates with an 8% higher population density. When combined with other geographic advantages, fertile soils and moderate climates near water, these factors create the planet's most crowded regions. The Indus River basin exemplifies this synergy. Covering just 0.3% of Asia's land area, it supports over 300 million people. Satellite images reveal uninterrupted nighttime lights stretching for hundreds of kilometers along the river. Similar patterns appear along the Yangtze, Nile, and Mississippi, demonstrating geography's invisible hand in shaping human settlement. Next, we'll explore how these river systems function as liquid highways, stacking survival advantages in specific locations that continue to draw people century after century. Liquid highways of civilization. Watch this time-lapse of nighttime lights along the Nile from 2000 to 2020. Witness the river's path as if beads on a string guiding civilization's journey. This pattern reveals why rivers act like nature's highways, solving 4 critical human needs in one geographic feature: fresh water, fertile soil, transportation routes, and waste disposal. Historical records confirm this advantage. 3/4 of ancient capitals emerged along major rivers. The Tigris-Euphrates system birthed 9 successive empires between 400 BCE and 500 BCE, while Rome's Tiber River transported 60,000 tons of grain annually at the empire's height. These weren't cultural choices but geographic necessities, as rivers enabled the movement of goods and sustained growing populations. The Ganges River illustrates modern river dependence. Its basin occupies just 0.1% of India's land area, but supports 400 million people, more than the entire United States population in a space smaller than South Carolina. The river deposits 1.84 million tons of nutrient-rich sediment daily across its floodplain, creating soil fertile enough to yield 3 harvests annually. Over 60% of India's irrigated farmland draws from Ganges water, producing staple crops that feed nearly half the country. Archaeologists trace urban civilization's origins to river advantages. The Tigris-Euphrates system enabled the first city-states by providing reliable irrigation for wheat and barley. Cuneiform tablets from Uruk detail how the river transported construction materials and traded goods. Records show the city imported 25,000 tons of stone annually via water routes, an impossible feat overland with ancient technology. Modern rivers face mounting pressures, highlighting the timelessness of river reliance. The Colorado River's flow has dropped 20% since 2000, failing to reach its delta in most years. 7 U.S. states and Mexico legally divide water rights, with allocations based on 1920s flow levels that no longer exist. Reservoirs like Lake Mead now operate at 30% capacity, threatening water supplies for 40 million people. Economic productivity still clusters near waterways. Global shipping data reveals that cities with river ports generate 18% more GDP per capita than inland counterparts. Germany's Rhine corridor handles 80% of the country's waterborne freight, while occupying just 7% of its land area. The Mississippi River moves 500 million tons of cargo annually, equivalent to 50 million truck trips. Agricultural yields demonstrate the clearest river advantages. UN Food and Agriculture Organization data shows farms within 10 kilometers of rivers produce 40% higher yields than those relying solely on rainfall. River irrigation allows double cropping where dry fields produce one harvest. Egypt's Nile Valley achieves wheat yields triple its desert farms just kilometers away. Water access explains population growth disparities. The UN's demographic reports show countries with major river systems maintain 2.1% annual population growth versus 1.3% for water-scarce nations. Ethiopia's Nile-dependent regions grow 3 times faster than its arid east. India's Ganges basin adds 8 million people yearly, equivalent to adding another London annually through natural increase alone. The Mekong River highlights emerging challenges. Its delta produces half of Vietnam's rice, while housing 18 million people. Rising sea levels now salinate 30% of delta farmland annually. Upstream dams reduce sediment flow by 70%, causing the delta to shrink rather than build elevation. These pressures force 500,000 residents to migrate yearly from formerly productive lands. Ancient river civilizations share modern lessons. Babylonian records show salinization destroyed Sumerian fields when irrigation dissolved mineral deposits. Today, the Indus Valley faces identical issues. 25% of Pakistan's irrigated land suffers from salt accumulation. Satellite images reveal fields abandoned where rivers shifted course centuries ago, foreshadowing modern climate impacts. Hydropolitical tensions mirror past conflicts. Mesopotamia's city-states fought over water access as early as 2500 BCE. Today, 60% of the world's major river systems cross international borders. Ethiopia's Renaissance Dam project reduced Nile flows to Egypt by 15%, threatening a country where 95% of people live within 20 kilometers of the river. Technology alters but doesn't erase river dependence. China's South-North Water Transfer project moves 45 billion cubic meters annually, equivalent to creating a new Yangtze tributary through concrete canals. However, this water costs 3 times more than local sources, limiting its economic impact. Desalination plants provide 50% of Israel's water, but consume 10% of national electricity. River resilience varies by geography. The Amazon's massive flow volume makes it relatively stable despite deforestation. Smaller systems like the Jordan River have lost 90% of their historic flow from overuse. The Aral Sea disaster proved terminal. What was once the 4th largest lake now supports zero commercial fishing where 40,000 workers once harvested. 50,000 tons annually. The dirt on dense populations. Under a microscope, fertile lush soil resembles nature's black gold, a rich tapestry of organic matter and mineral fragments alive with microbial activity. In stark contrast, desert sand looks barren, like a sea of uniform quartz grains with empty spaces between them. This difference underscores why soil quality forms the invisible backbone of human settlements. Only 11% of Earth's land surface is naturally arable, yet this slim fraction must sustain nearly 8 billion people. Ukraine's Chernozem soil highlights this critical role. Covering just 1.5% of global farmland, these black soils produce 15% of the world's wheat exports. A single square meter of Chernozem teems with life, up to 50 earthworms and 10 billion bacteria constantly replenishing nutrients. Geology often shapes unexpected population hubs. Java, for instance, occupies just 7% of Indonesia's land area, but supports 60% of its population, thanks to volcanic andesol soils. These soils retain nutrients like phosphorus 3 times longer than others, enabling year-round rice cultivation. Similarly, Rwanda's volcanic highlands sustain population densities triple the African average, with farmers thriving on just 0.1 hectares each. Australia's interior tells the opposite story. Over 70% of the continent suffers from nutrient-poor soils, a legacy of 100 million years without significant geological activity. Wheat yields here average just 1.7 tons per hectare, compared to 3.5 tons in Chernozem regions. This explains why 85% of Australians live near the coast, where marine deposits enrich the soil. Soil degradation often forces migration. During the American Dust Bowl, 2.5 million people were displaced as topsoil erosion reached catastrophic levels. Today, northern China loses 3 billion tons of topsoil annually to wind erosion, driving rural populations into cities. In sub-Saharan Africa, 65% of farmland suffers nutrient depletion severe enough to slash crop yields by up to 50%. The UN Food and Agriculture Organization warns that 33% of global soils already face moderate to severe degradation. At current rates, the world loses 24 billion tons of fertile soil annually, equivalent to removing 12 million hectares from production. In regions like the Sahel, agricultural capacity could drop by half by 2050 if these trends persist. Volcanic soils offer temporary advantages. Iceland's 1783 Loki eruption deposited ash that tripled barley yields for a decade. But most volcanic soil benefits accumulate over millennia. The Nile Delta, for example, took 30,000 years to build its 20-meter-deep fertile layer, which modern farming now depletes faster than it can replenish. Soil chemistry also sets limits. Australia's outback contains iron oxide that colours its sands red, but lacks essential nutrients like nitrogen and potassium. Southeast Asia's peat soils store vast amounts of carbon, but turn acidic when drained for farming. Brazil's Cerrado region required 50 million tons of lime treatment before becoming productive. Irrigation can exacerbate soil depletion. Pakistan's Indus Valley loses a meter of topsoil every 25 years due to waterlogging and salinity, issues first documented in Babylonian records 4,000 years ago. California's Central Valley faces similar challenges, with 10% of irrigated land now showing elevated salinity that reduces yields. Restoration efforts show promise but face limits. China's Loess Plateau project restored 35,000 square kilometers through terracing and vegetation, but it took 15 years. Cover cropping can rebuild topsoil at just 1 millimeter per year, far slower than the 10 millimeters lost in a single dust storm. Temperature and soil depth further shape human settlement. The American Midwest combines fertile mollysols with an ideal climate for staple crops, supporting 127 million people on just 15% of U.S. land. Meanwhile, Africa's laterite soils, often just 20 centimeters deep, limit agricultural potential. In contrast, India's Gangetic Plain offers near limitless rooting depth, enabling water-intensive crops like sugarcane. Urban expansion directly competes with prime soils. Ontario lost 18% of its best farmland to urban sprawl between 1996 and 2016. China's urbanization consumes 400,000 hectares of productive delta soils annually. Once paved, these ecosystems take centuries to recover. The coming decades will demand tough choices. The FAO projects global food demand will require 593 million hectares of new farmland by 2050, much of it on marginal soils requiring immense energy inputs. Balancing soil preservation with human needs will define the future of agriculture. The Goldilocks climate principle. This thermal map reveals a striking pattern. Human populations cluster tightly around specific temperature ranges. The ideal annual mean temperature for dense human habitation falls between 11 to 15 degrees Celsius, often referred to as the Goldilocks zone for its balance of comfort and livability. This narrow band covers just 11% of Earth's land surface, but contains over 50% of the global population. Consider the United States as an example. Nearly 70% of Americans live between 35–45 degree N latitude, where average temperatures remain within this comfort zone. In contrast, population densities drop sharply in southern states like Florida and Texas, where annual means exceed 20 degrees Celsius, and in northern states like North Dakota, where temperatures average below 5 degrees Celsius. California's Central Valley, with its year-round mean of 14 degrees Celsius, exemplifies the Goldilocks zone, supporting both dense populations and some of the highest agricultural productivity nationwide. Europe's development history also highlights the importance of climate. The Gulf Stream keeps winter temperatures 10 degrees Celsius warmer than similar latitudes in Canada, enabling early agricultural settlements in Norway at 60 degrees north, a latitude where much of Canada remains uninhabited. England's average annual temperature of 10 degrees Celsius allowed for year-round farming and higher population densities compared to Mediterranean regions with hotter, drier summers. Even the Roman Empire's expansion aligned with the 14 degrees Celsius isotherm, as grapevines, a key agricultural marker, thrived within this range. The Sahara Desert, on the other hand, demonstrates the exclusionary power of extreme heat. With an annual mean of 30 degrees Celsius, it supports just 2.5 million people across 9 million square kilometers, a density 200 times lower than temperate Europe. Satellite data reveals that Saharan populations cluster around oases, where groundwater moderates local temperatures. The desert's edge forms one of the sharpest demographic boundaries on Earth, with population densities plunging from 500 people per square kilometer to under 1 within just 100 kilometers. Temperature extremes also impose physiological and economic limits. Human metabolic rates must increase 10 to 15% to maintain core temperature in environments below 5 degrees Celsius or above 35 degrees Celsius. This helps explain why Canada's population remains concentrated within 200 kilometers of the U.S. border, despite the country's vast northern territories. Similarly, studies of military outposts show personnel require 40% more calories in Arctic conditions compared to temperate bases. Worker productivity drops 2% for every degree above 27 degrees Celsius in manufacturing jobs, while cognitive test scores decline 13% in unair-conditioned classrooms during heat waves. Agriculture is even more sensitive to thermal boundaries. Corn, for instance, requires at least 120 frost-free days, a limit that currently falls at 55 degrees north in Europe but only 48 degrees north in colder North America. Wine grape cultivation aligns with the 14 degrees Celsius annual isotherm worldwide. As the IPCC projects this thermal niche to shift 300 kilometers poleward by 2050, new agricultural zones may emerge in previously marginal lands. Urban infrastructure further reflects climate adaptations. Canadian cities allocate 5% of municipal budgets to snow removal, an expense absent in warmer regions. Phoenix requires 35% more electricity per capita than Seattle for summer cooling. Moscow's buildings feature triple-pane windows and thicker insulation, while Barcelona's structures are designed for milder winters. These adaptations create economic friction, discouraging population dispersal beyond optimal temperature zones. Historical climate shifts under these patterns. During the medieval warm period, 9501-250 CE, Viking settlements thrived in Greenland as temperatures rose 2 degrees Celsius above modern averages. Conversely, the Little Ice Age, 1300 to 1850 CE, saw these colonies fail as growing seasons shortened. The Maya civilization collapsed during regional droughts when temperatures increased just 1 to 2 degrees Celsius, changes comparable to current projections. Modern climate refugees face similar challenges. In Bangladesh, rising sea levels displace 300,000 people annually toward cooler inland areas. Alaska native villages like Shishmaref are relocating as warming permafrost destabilizes coastal foundations. The World Bank estimates climate change could displace 140 million people within countries by 2050, with most movement toward temperate highland zones. These thermal constraints shape economic outcomes as well. U.S. counties with annual means between 11 to 14 degrees Celsius report 30% higher GDP growth than hotter or colder counterparts. European regions in this thermal sweet spot attract 40% more technology investment than areas just 5 degrees Celsius warmer or cooler. As the Goldilocks zone shifts 500 kilometers poleward this century, the geographic advantages that have shaped human settlement for millennia will be rewritten. the inland exceptions that prove the rule. These satellite images reveal striking inland hubs thriving against the odds, defying the dominance of coastal cities. Moscow, with its radial growth centered on the Moskva River, and Denver, perched at the meeting point of the Great Plains and Rocky Mountains, exemplify how engineered connectivity can overcome natural isolation. Moscow's 12 million residents cluster within 10 kilometers of the river, while Denver's 3 million benefit from its strategic location at the 39th parallel, leveraging transport routes and energy resources. These cities show how geography, when paired with human ingenuity, can rewrite the rules of urban success. Take Chicago, for example. Its rise wasn't inevitable, but engineered through its position linking the Great Lakes and the Mississippi River via the Illinois waterway. The 1848 Illinois-Michigan Canal slashed transport costs by 80%, fueling explosive growth. This pattern repeated in other inland hubs like St. Louis, where the Mississippi and Missouri rivers meet, and Minneapolis, where the Mississippi becomes navigable. Railroads later reinforced these cities' roles, with Chicago becoming the terminus for 13 major lines by 1890. The region's fertile soils provided agricultural surpluses that supported urban growth, proving that inland cities could thrive without direct coastal trade. Moscow's story further illustrates this theme. The Moskva River's winding course provided early settlers with drinking water, transportation, and even defensive moats for the Kremlin. By the 18th century, canal systems transformed Moscow into Russia's port of five seas, connecting it to the Volga, Don, and Baltic White Sea systems. Today, the riverfront, though only 3% of the city's area, generates 25% of its economic activity, with land values near the river averaging $4,500 per square meter, nearly 4 times higher than areas just 5 kilometers inland. Moscow's success underscores how strategic infrastructure can anchor development far from the coast. But not all inland cities share this fortune. Kazakhstan's capital, Astana, now Nur-Sultan, relocated 1,200 kilometers from the nearest ocean in 1997 as a political statement. Despite $100 billion in infrastructure investment, the city remains heavily reliant on air links for 80% of its imports. Similarly, Bolivia's La Paz, the world's highest capital, faces unique challenges, spending 15% of its budget on oxygen enrichment for government buildings. These cities, surrounded by uninhabited hinterlands, highlight the difficulties of thriving without natural geographic advantages or robust transport networks. Yet, transportation corridors can redefine inland value. France's high-speed TGV network transformed Lyon into a 2-hour commute from Paris, boosting its population by 18% since 2000. China's Wuhan, a major rail hub on the Yangtze River, handles 20% of the nation's freight tonnage. Denver International Airport, with its 6-runway configuration, serves 70 million passengers annually, proving that infrastructure can overcome geographic isolation when investments reach critical thresholds. Historical examples reinforce this pattern. Vienna thrived at the intersection of Danube River trade routes and the Amber Road. Timbuktu became the Sahara's port, where camel caravans met the Niger River. Samarkand flourished by controlling Silk Road mountain passes. Each case relied on multiple transport modalities converging, a lesson modern planners replicate with intermodal hubs like Chicago's O'Hare or Dubai's inland ports. Inland cities thrive when they combine strategic location, resource wealth, and engineered connectivity. Chicago handles 25% of U.S. freight, Moscow contributes 22% of Russia's GDP, and Denver dominates U.S. energy trading, all without coastal proximity. These exceptions celebrate human ingenuity, proving that with the right investments, even the most isolated locations can flourish. The Future Human Map. This interactive globe invites you to explore the future of human settlement, layering 2,100 population projections onto today's geographic features. By synthesizing water availability, agricultural potential, climate resilience, and infrastructure development, it identifies prime zones that will shape where humanity thrives or struggles. These zones, covering just 12% of global land, are projected to house 75% of the population by century's end. But what will a future map of human settlement really look like? Water scarcity emerges as a defining factor. Take the Middle East's Euphrates-Tigris basin. Turkey's dam projects have reduced downstream flows by 40% since 1990, leaving Syria's irrigation networks at 60% capacity and shrinking Iraq's marshlands from 20,000 to 2,000 square kilometers. Population growth compounds the strain. 50 million more people are expected in the basin by 2050, while renewable water supplies drop by 25%. Current treaties allocate fixed water volumes, but climate models suggest these agreements will soon become physically impossible to uphold. What happens when the water simply isn't there? Climate migration corridors offer another striking pattern. Sub-Saharan Africa shows clear pathways, with millions moving from the Sahel toward coastal West Africa and the Congo Basin. By 2050, 85 million people could relocate along these routes. In Asia, rising seas in Bangladesh may displace 15 million toward India's Ganges Basin. These recipient zones will need 300 to 500% more infrastructure investment to absorb such flows without destabilizing. The question is, can these regions adapt fast enough? Meanwhile, abandonment zones tell a different story. Florida's low-lying coastal counties could see population declines of 30 to 50% after 2060, while saltwater intrusion threatens 20% of the Nile Delta's farmland. Satellite imagery already shows these shifts. Miami Beach home values in flood-prone areas have dropped 25% since 2015, even as property booms elsewhere. Structured retreat could save $1 trillion compared to chaotic abandonment. But will governments act in time? Infrastructure investment becomes critical in this context. The model identifies 15 global adaptation corridors requiring urgent attention, such as Nigeria's Middle Belt, India's Deccan Plateau, and the American Upper Midwest. Successful projects share three traits: multimodal transport links, decentralized renewable energy grids, and scalable water systems. Without these, migration pressures could overwhelm receiving areas. Political power is also shifting. India's Ganges Basin, projected to house 800 million people by 2075, could control 25% of the nation's water resources. Ethiopia's control of the Blue Nile headwaters enables hydropower exports to Sudan and Egypt, reversing traditional power dynamics. These changes highlight how geography will increasingly dictate influence. Adaptation strategies vary widely in effectiveness. Singapore-style water recycling scores highest at 8.7/10 for resilience, but requires $500 per capita annually, unaffordable for most nations. Dutch-style coastal defenses rate 7.2/10, but come with $200 billion price tags for delta regions. Inland migration corridors score just 4.3/10 due to conflicts in receiving areas. Layered approaches, like Vietnam's combination of Mekong Delta dikes and highland urban expansion, achieve moderate success at 6.8 out of 10. Water treaties offer a glimmer of hope. Jordan and Israel's 2021 water for energy swap serves as a model. Solar power exports to Israel offset desalinated water imports to Jordan. Similar agreements along the Nile could reduce conflict risk by 40%, showing how cooperation might ease tensions. The stakes are enormous. The model estimates $120 trillion in global real estate value sits in high-risk zones, yet only 15% of this is priced for climate risk. As the climate transition redefines advantage, the question remains, will we adapt in time, or will geography dictate our future? These two maps tell the story. In 1900, 60% of humanity lived within 100 kilometers of coastlines or major rivers. By 2100, Just 40% will remain in these zones, with new clusters forming in climate-resilient inland areas. Rising seas displace populations from deltas, while warming opens northern latitudes. The Nile and Ganges will still support millions, but new cores emerge around systems like the Great Lakes and Congo Basin. Geography's rules endure. Water access and temperate climates shape density, but their boundaries shift. Thriving depends on how we adapt. How will you read this new terrain?